Here, this circuit shows the bridge full wave rectifier. Here, this circuit shows the bridge full wave rectifier. In this circuit, here this is a step-down transformer similar to your half-wave rectifier. What is the use of the step-down transformer? Here, the diode requires less amount of voltage. By using this step-down transformer, we are going to decrease the voltage from 230 volts to the required voltage for these diodes. That is the reason why we are going to use this step-down transformer. Here, this is the connection for your total bridge full wave rectifier. In this case, we are using the 4 diodes. In this case, we are going to use the 4 diodes. Whereas in the case of half rectifier, 1 diode. In the case of full wave rectifier, 2 diodes. Now here, bridge full wave rectifier, it is 4 diodes. Now here also we are going to observe the output across the load resistance. Output across the load resistance. Either it may be a voltage or current. Output voltage, output current, both are observed across this load resistance, similar to your half wave rectifier as well as full wave rectifier. In all these rectifiers, we are going to observe the output voltage, output current across this load resistance. Okay. Now here, when you are giving the positive half cycle, that means here during positive half cycle, A positive, B negative. Here, A positive, B negative. Previously I said that. In previous classes also I said that when you are giving the positive half cycle, during positive half cycle, A positive, B negative. Because of that, see here how the diodes are connected, whether it is forward bias or reverse bias. Now here, positive of your transformer secondary is connected to the D1 anode, and positive of your transformer secondary is connected to the D4 cathode. Because of this, D1 in forward bias, D4 in reverse bias. Here, positive connected to anode of D1, forward bias. Positive connected to cathode of D4. So here, D4 is in reverse bias. That means you can remove this D4. Similarly, here negative. Here negative is connected. Transformer secondary negative is connected to the D2 cathode. Here D2 cathode like this. D2 cathode. That means it is in forward bias. Similarly, negative of your transformer secondary is connected to the anode of D3. Here like this. D3 anode. So here D3 is a reverse bias. That means you can remove this. It is in reverse bias. Okay. So in this case, D3, D4 both are in the reverse bias. So that's why these are in the opened. Here D3, D4 both are in open. That means ID3, ID4 both are 0. In the case of positive half cycle, ID3, ID4 is 0. Then what is the current direction in this case? Now here current flow to the diode D1. Current flow from positive of your secondary transformer to the diode like this, and after that it comes to the load resistance like this. Here positive to diode D1, and after that load resistance, and after that it moves like this, and after reaching this node it comes back to the D2. Like this. D2, and after that negative of your B. After that negative of your B. Now this is the current direction. Here positive to the diode D1. See the direction. Carefully see the direction. Positive to the diode D1, and after that load resistance, and after it moves like this, and upward direction, and after D2 to the negative of your transformer secondary. Now the current travels from positive to negative like this. Okay. Here this is called overlap, and this is called overlap. That means there is no connection between this line and this line. There is no connection between this line and this line. So that's why current directly travel towards negative of your transformer secondary. Now this is the direction of the current in the case of positive off cycle. Similarly, when you are giving negative off cycle, when you are giving negative, when you are giving the negative off cycle, here during one second, one more, just 1 second. It's 508. What happened? It's 508. What happened? Do you have any doubts? If you have any doubt, please keep here. 508. Okay, no doubts. Okay. During negative off cycle, here during negative off cycle, A negative, B positive. Here, when A is negative, what will happen to this D1 and D2? Negative off cycle is connected to the D4 cathode. Here, negative connected to D4 cathode. D4 cathode. So it is in forward bias. Similarly, negative connected to D1 anode. So here D1 is in reverse bias. D1 is in reverse bias. So it is opened. So here D1 is in reverse bias. So it is in open condition. Similarly, positive. Here positive connected to D3 anode. Here positive connected to D3 anode like this. So D3 is in forward bias. Similarly, positive connected to D2 cathode. Here D2 cathode. So here DT is in reverse bias. DT is in reverse bias. So again D2 also removed from the circuit. Right? Because it is reverse bias. So in the case of negative off cycle, D1, D2 both are open. So that's why ID1 is equal to IDT is equal to 0. Then how the current is travel here? How the current is going to travel? Now here from positive here. From positive, the current is flowing like this. Here from positive to D3. From positive to D3 like this. D3 like this. Last 10 minutes. From positive to D3 like this. And after that, it moved towards load resistance in downward direction. Load resistance in downward direction. And after that, it moved towards like this. And after that, here there is a overlap. Here there is a overlap. This overlap to the D4. It moved towards D4. From overlap to the D4, it is going to move here. Positive to, here it is overlapping. That means there is no connection between this line and this line. So positive to the D3, D3 the load resistance, and after it moved like this, and after move towards upward direction to the D4, and come back to the negative of your A like this. Now this is the current direction in case of negative off cycles here. Once again I am explaining. Positive to the D3, D3 to the load resistance, and after D4, thereafter negative of your transformer. This is the current direction. Now here in both the cases, current is in downward direction. If you observe here, in positive off cycle, in negative off cycle, in both the cases, current is in the downward direction. Note this point. Okay. Now see here how to draw this waveform. Similar to your Fullwave rectifier. These waveforms are similar to your Fullwave rectifier. Here, these are your positive off cycle. During positive off cycle, D1, D2 both are on. Here, during positive off cycle, D1, D2 both are on. During negative off cycle, these are negative off cycle, D3, D4 are on. Now I am drawing this ID1, ID2. Now this is the current ID1, ID2. Why? Because D1, D2 both are on in the case of positive half cycle. So that's why these are your ID1 and ID2. Similarly, here these are your ID3, ID4. Why? Because in the case of negative half cycle, ID3, ID4 is on. In the case of negative half cycle, ID3, ID4 are on. In the case of positive half cycle, ID1, ID2 both are on. See here, this is your ID1, ID2 waveform. This is your ID3, ID4 waveform. Now, total current, nothing but current to the load resistance, is given by this current plus this current. That means ID1, ID2 plus ID3, ID4. So here, this is a total current through the load resistance. Why? Because both are in the same direction. See here, both are in the same direction. These two currents. In the case of positive half cycle, negative half cycle, both the currents are in the same direction. If the currents are in the same direction, we are going to add the currents. So that's why I'm adding this current and this current, this current and this current, this current and this current. Positive plus 0, positive. 0 plus positive, positive. Positive plus 0, positive. 0 plus positive, positive. Positive plus 0, positive. 0 plus positive, 0. Like this, this is a current to the load resistance. Similarly, how to draw the voltage of load resistance? V is equal to I into R. V is equal to I into R. Here, this is I into resistance. Again, you are going to get a positive half cycle. This is your I, again resistance. This is I, again resistance. Again, you are going to get a positive half cycle. So, this is the voltage, positive into resistance. Okay, this is total about your bridge full wave rectifier. Now, here, in the case of half wave rectifier, the output is like it is pulsating DC. It is pulsating discontinuous DC. Why? Because positive 0, positive 0, positive 0. In the case of half wave rectifier, the output may be looking like this. So, in the case of half wave rectifier, the output is discontinuous pulsating DC. Whereas in the case of full wave rectifier, the output may be like this. That means it is continuous pulsating DC. Now, in the case of bridge full wave rectifier, see here, in the case of bridge full wave rectifier, also same waveform. That means continuous pulsating DC. Okay. Now, these are different in the case of half wave full wave and bridge full wave rectifier. In the case of half wave rectifier, the output is discontinuous pulsating DC. In the case of full wave rectifier, continuous pulsating DC. In the case of bridge full wave rectifier, also continuous pulsating DC. Okay. Whereas in the case of half wave rectifier, by using one diode, we are converting the AC into the discontinuous pulsating DC. In the case of full wave rectifier, we are using the center tapped transformer. By using center tapped transformer and two diodes, we are converting the AC signal into the continuous pulsating DC. Whereas in the case of bridge full wave rectifier, again we are using the step-down transformer and four diodes. By using this, we are converting the given AC into the continuous pulsating